Okay, I am back. And we're going to continue with an example here. So, as you will see, our examples are going to get more and more complicated. And after we finish these properties, we're going to see how we can take inverse Laplace transformations. And the experience that we're going to have in these properties are going to help in our taking inverse Laplace transformations. So let us continue with an example. Sorry, this is finished. So our f of t that we have to find the Laplace transform of is given as e to the minus at sine omega t when t is larger than or equal to 0. And here I'm going to be assuming that a is positive. Okay? So here, as you see, I have when a is equal to 0, I would have e to the minus at equal to 1. So I would have sine omega t, a pure sine, neither decaying nor growing. So the first thing that I'm going to do is to explain what this signal, what this function of time would look like. We are going to be encountering such functions in our investigation of control systems. So here is what I'm going to do. I'm going to draw e to the minus at first. A is positive, so this exponential is decaying here. Okay, it is going to be starting, it is starting at 1 and it is decaying exponentially. And the second thing that I have is sine omega t. So I would have a sine function which is oscillating. And this f of t function is just a multiplication of these two functions. And I would like to find what the multiplication is. First of all, at the zeros of the sine function, the multiplication will again going to be equal to 0. Therefore, here I need to keep the 0 crossings here at this function. So I have here the function is going to multiplication is going to be starting from here, and then it's going to be making something like this. It's going to be crossing like that, and I would have a decaying sinusoid like this. Okay, so when I have minus at here, when a is positive, I would have a decaying sinusoid, because this decaying exponential is going to modulate the amplitude of the sine function. So as the exponential decays, the maximum amplitude of the sine function is going to be decaying. Okay, it's going to be smaller and smaller at each time instant. Therefore, I would have a decaying sine function here, which is e to the minus at sine omega t. So we are required to find what the Laplace transform of this function is. Here I have 1, and this is time axis. So in order to be able to do that, I will use this property. E to the minus at times f of t is going to be f of s plus a. For that, I need to remember what the Laplace transform of sine omega t is. So do you still remember? So I have sine omega t. In Laplace domain, it is omega over s squared plus omega squared. And I know that according to this property, if I want to find the Laplace transform of e to the minus at sine omega t, then here I need to substitute s plus a. Okay? So let us substitute s plus a. E to the minus at sine omega t is going to be in f of s, in the original Laplace transformation, which is this one here, I need to substitute s plus a instead of s. Alright? So this is going to be omega over, instead of s square, I have s plus a square plus omega square. Okay? So this is the Laplace transformation of this function. So when you add some constant into to s, here, we see that in time domain that looks like a decaying exponential. If I add a positive constant, positive real constant to s, in time domain it is a decaying exponential, multiplicative decaying exponential. So now we are going to be looking at the poles of such a Laplace transformation. We see that we don't have any zeros for this Laplace transformation, but we have some, of course, poles. And how many poles? In this case, this is going to give me a second order polynomial. That means that I will have two poles, and I can find them by equating the denominator polynomial to 0. So here I will take minus omega squared to the other side, and then I will take square root of both sides. It is going to give me s plus a equals to plus minus j omega, and therefore the poles are at s12 is equal to minus a. Here I would have plus minus j omega. These are the pole locations of this Laplace transformation. So think about whether these poles are in the left half plane or right half plane. Left half plane is the part of the complex plane with negative real parts. Right half plane is the part of the complex plane with positive real parts. In this case, the real parts of these poles are minus a. A is positive, therefore the real parts are negative. Therefore, these poles are to the left of the imaginary axis. They are in the left half plane. Okay? So let us draw the complex plane, real of s, imaginary of s. And I will first mark minus a. This is the real part of the poles, and they are going to have imaginary parts plus omega j and minus omega j. So plus j omega minus j omega. So I would have here the pole locations. Okay? Now here there is an intuition that you need to gain from such a picture. If the poles are on the left, if all poles are in the left, then the time function is going to be decaying towards 0. Okay? If all poles are on the left. Here, all poles are on the left, therefore this function is decaying towards 0. All right? If all poles are real, in this case, I don't have real poles because they have non-zero imaginary parts. If all poles are real, then there won't be any oscillations in the function. In this function, there is definitely an oscillation, okay? Because it doesn't have real poles. Then if there are some complex poles with non-zero imaginary parts, then that means you would have oscillation. Okay? And here we see that an oscillatory time function which goes to 0 as time goes to 0. What causes this function to go to 0 as time goes to 0? And the answer of that question is that sine is never going to 0. It is always non-zero, oscillating, but this exponential is decaying to 0. Therefore, this part is causing this function, this red function, to go to 0. And you see that if a is negative, then if a is positive, then I would have a negative number here, and that negative number becomes the real part of the poles. In the left half plane, real parts of the poles are always negative. In the right half plane, complex plane, the real parts of the poles are always positive. So now we are going to be looking at a very, very similar function, except that I will take these poles to the other side. So I will take the poles to the right half plane, and then you will see the opposite behavior. What is the opposite behavior? Behavior of going to 0 is I will have the opposite of that. All right? So the sine will not decay anymore, but it's going to grow in magnitude. That is all dependent on whether the poles are in the left half plane or they are in the right half plane. So here let us look at the function f of t is equal to e to the at sine omega t, and t larger than or equal to 0, a is still positive. And in this case, we have a growing exponential here. As time goes to infinity, it grows like this. So when I change the magnitudes of the signs with that exponential function, the sign is going to be growing. All right? So here let us try to draw this function. I will again try to draw a similar figure. So this is my exponential. It is going towards infinity if a is positive. And the sine function is the same. It's changing like this. Okay? The amplitude is 1. And what happens when I multiply these two functions? In that case, the amplitudes of the sine function are going to be multiplied. They are going to be modulated by this growing exponential here, and that is going to make the sine grow as well. But how is it going to grow? Do you think it's going to grow like this? So is it going to grow like this, for example? Think about it. So here I'm multiplying these two functions. Therefore, if one of the functions is equal to 0 at some point, then the multiplication is going to be still 0 at the same point. Therefore, here I need to keep the 0 locations here at the same points. So here this function is always positive, but you see that I get sine functions negative at some time, and exponential is always positive here. So the multiplication should give me a negative number as well. So therefore it's not going to be looking like this. The true multiplication is going to be looking like this. So I would have a sine function, and the 0 crossings would still be at the same point here, but the sine magnitudes are going to be growing. Okay, so I would have something like this, and it's going to be growing and growing. All right? So maybe I should emphasize this curve just a little bit. So you need to understand that there is no oscillations here. I'm doing this for it to be seen in the video in a better way. So the function is growing in magnitude. So this is a function that oscillates with growing oscillation amplitudes. Now I can actually look at the pole locations, but first let us calculate the Laplace transformation of this function. So sine omega t is again the same thing, but now instead of e to the minus at, I have e to the at. Okay? So instead of substituting s plus a here, I need to substitute s minus a. Because here, if I substitute a is equal to minus a, then I need to get this thing. Okay? So the Laplace transformation of e to the at sine omega t is going to be omega. Here I will substitute s minus a instead of s. Okay? Now, where are the pole locations of such a function? So here, if I equate the denominator to 0 and try to solve for s again, I will do the same thing. I will just have a minus sign here instead of a plus sign. Therefore, the result is going to be, instead of minus a plus j omega, the result will be a plus minus j omega. Okay? So the pole locations are plus a plus minus j omega. And if I mark them on the complex plane, I would have plus a here and plus minus j omega. The pole locations will be here. Now they are in the right half plane. What does that mean? That means that I will have multiplicative growing exponentials here. I have a right half plane pole here, and that means that I have multiplicative growing exponentials. So these oscillations are going to be growing. And how do I know that there are oscillations? Because there are poles with non-zero imaginary parts. This is j omega, and this is minus j omega. Okay? So by immediately looking at the pole locations, so you don't really need to know this function anymore. If you know this Laplace transformation, you will be able to guess or estimate the form of the function that you are dealing with by looking at just the pole positions here. So this finishes the third property. Now we're going to go into the fourth property. We have 5 properties in total, so this is the second last one. So the fourth property tells us that Laplace transform of t times f of t is equal to minus d over ds, capital F of s. Okay? First, I will try to make you understand what this property is saying. So in this case, again, I have the function f of t and the Laplace domain function, capital F of s. In this case, instead of multiplying the function with an exponential, I'm multiplying the function with a polynomial, which is equal to t. Okay? T times f of t, then it has the Laplace transformation, minus d over ds, capital F of s. Okay? So multiplication by t in time domain corresponds to the negative derivative with respect to s in Laplace domain. Multiplication by t in time domain corresponds to a negative derivative with respect to s in the Laplace domain. So here, let me try to show this property. So I know that f of s is the Laplace transform of f of t. So I would have just this thing. Sorry, I'm overwriting here t. Infinity, and I have f of t e to the minus st dt. Okay. Clearly, both sides are a function of s. And now I'm going to calculate the derivative, d over ds, f of s. I will calculate this derivative and try to understand what is going to come out. So this is d over ds of this integral. Okay? F of t e to the minus st dt. Integration is with respect to t. And s is just a constant for the integral. So I can actually take this d over ds inside. All right, inside the integral. So I would have 0 to infinity. So I have d over ds, f of t, e to the minus st dt. I just took the derivative inside the integral because the integration variable is independent of the derivative variable here. Of course, if the variables were the same, this wouldn't make any sense. So here I'm trying to take the derivative with respect to s of such a function. Here, with respect to the derivative variable s, t is just a constant, okay? So this f of t is nothing but a constant for this derivative operator, okay? So I can actually take this f of t outside the differentiation because it's just a constant with respect to s. And the resulting thing is going to be just the derivative of this exponential with respect to s, okay? So that is going to be 0 to infinity. F of t is just a constant with respect to s. I took it out of the differentiation, and then I take the derivative of e to the minus st with respect to s. And that is going to give me derivative of this thing with respect to s is going to be minus t times the exponential itself. Because the derivative of the exponent with respect to s is minus t, e to the minus st dt. Okay? Now here there is minus t. I can take the minus sign outside. And I can take t in front of f of t. 0 to infinity t f of t e to the minus st dt. And there is a minus sign here. Okay? And what is this? What is this new integral? If I call this function g of t, then this is the Laplace transformation. Think about the definition of the Laplace transformation. This is the Laplace transformation of g of s. Okay? This is the Laplace transformation of t f of t. Okay? And therefore here this is negative Laplace transformation of t f of t. Okay? So I get the equation d over ds f of s is Laplace transformation of, it is a negative Laplace transformation of t f of t. Okay? Multiplying both sides with minus 1 is going to give me this. Laplace transform of t f of t is equal to minus d over ds capital F of s. Okay, but that is just our property. So now let us look at some examples. So I would have here the following function. F of t is equal to t for t larger than or equal to 0. So this function also has a specific name in control theory, and it is called the unit ramp function. So if I try to draw it like this, then I have f of t here. It is 0 again before time t is equal to 0, and it is t as for larger times than 0. Okay? So here the slope is 1. This is called a ramp function in control theory. So the name of this thing is unit ramp function. Ramp in Turkish is rampa, which is what this looks like. All right? So here the question is, what is the Laplace transformation of this thing? All right? So by using this property, it's really not very difficult. So here, this f of t, as you see, is t times 1. Okay? So I multiply the unit step function with t to obtain the unit ramp function. That means that I need to first write the Laplace transformation of unit step function. Then t times 1 is going to have the Laplace transformation d over ds, negative derivative with respect to s, 1 over s. Okay? So this is what this property is telling us. So now in order to be able to find the Laplace transform of the ramp function here, I need to take the derivative of 1 over s with respect to s and multiply it with a minus sign. So here I'm just going to be writing this like this. Minus d over ds, s to the minus 1. Okay? Now derivative of s to the minus 1 with respect to s is minus 1 comes into the front, and I have s and I subtract 1 from this power here. And that is going to give me minus 1. This one comes here, and then I have s to the minus 2. These minus 1s are cancelling each other, and I would have 1 over s squared here, which is s to the minus 2. Therefore here, the unit ramp function t has the Laplace transformation 1 over s squared. So think about the pole 0 plot for such a function. Does it have any zeros? So if you look at the denominator, if you look at the numerator, you see that it is 1. So we don't have any zeros, obviously. But we are going to have poles. And how many poles do we have for the unit ramp function, 1 over s squared? So we see that this is a polynomial again. So d of s is equal to s squared. It is again a polynomial, and it's a second order polynomial. That means that we need to have 2 poles again. Where are these 2 poles? These 2 poles are at the solution of this equation, 2 solutions of this equation, and that is going to be the same position everywhere. S1 is equal to 0, S2 is equal to 0. Therefore, if I draw the pole 0 plot for this Laplace transformation here, I'm going to have double poles at the origin. Okay? Unit step function has a single pole at the origin, and unit ramp function has double poles at the origin in the complex plane. Let us obtain another example. So in this case, I will use f of t is equal to t squared. So I multiply the unit ramp function once more with t. So the question is the same. F of s is a question mark. So here I would have this f of t squared is nothing but t times t. So I multiply the unit ramp function once again with t. I know that the unit ramp function t has the Laplace transformation s squared, or s to the minus 2 here. Okay? And then what is t times t? What would be the Laplace transform of that? Obviously, using our formula, minus derivative with respect to s times the Laplace transform of t here. Okay? Whatever function I multiply t here, I put the Laplace transform of it here in front of the derivative. So this is s to the minus 2. So I need to take the derivative of this s to the minus 2 with respect to s and multiply it with minus 1. Then it's going to give me the Laplace transform of t squared. All right? So here, if I take this derivative, minus 2 is going to come to the front. So I would have, this is equal to minus 2 is going to come to the front, and this is going to be s to the minus 3. All right? These minuses are canceling each other, so I have 2 over s cubed. And I think you can guess what the pole 0 plot of such a function would look like. So how many zeros would it have? In this case, because the denominator is a non-zero constant, we would have 0 zeros, and the denominator is just s cubed, so I need to have 3 poles, and that means, and if I equate this denominator to 0, I would see that all of the 3 poles would be at the origin. Okay? So this thing, the same pole 0 plot, except that I would have 3 poles at the origin. All right? Okay, let us get more complicated. For example, so we have f of t is equal to t times sine t. Let us say t times sine omega t. Okay? And this is true for t larger than or equal to 0. What is f of s? What is the Laplace transformation of this function? So again here you see that the sine t, which is a constant amplitude sinusoid, is multiplied with t. So we modulate the amplitude of sine with the function t. So let us try to imagine that function. So I would have t and f of t here. Sine omega t is like this, and t is something like this. So we multiply these two functions. Again, I need to keep the zero crossings here, but the amplitude of the sine is going to grow here. Okay? So let us make the amplitude grow. So it is going to be looking like this. The amplitude is going to be growing. All right? So maybe in the video it's not shown in a nice way. I can make it thicker like this. So the amplitudes are growing, but the zero crossings are remaining the same. Here in my plot, there is a slight shift in the zero crossings, but that is a mistake. The zero crossings should be exactly at the same places. So in this case, what is the Laplace transform of this function? So I would have, in this case, I need to look at the Laplace transformation of sine omega t. It is going to be omega s squared plus omega squared. So we see that if I multiply this one with t, then I need to take the derivative of this thing with respect to s. In order to be able to take the derivative, I will write this thing as like this, which is the same thing. Okay, but it's going to make the taking derivative easier. So here, t sine omega t is going to have the Laplace transformation minus d over ds omega s squared plus omega squared to the minus 1. So here this omega is just a constant with respect to the differentiation operator. So I can take it out, and this is going to be d over ds minus, sorry, this is going to be minus omega d over ds s squared plus omega squared to the minus 1. So let me take the derivative of this thing. I have some function of s taken to the power of minus 1. This minus 1 will come to the front, and I would have minus 2 here. And then I will take the derivative of the inside, the parentheses, with respect to s. Okay? So minus omega, and I have minus 1 times the same thing to the power minus 2, and derivative of inside with respect to s, which is 2s. Okay? Now let us write this thing. The minuses are cancelling each other. So I would have 2s omega divided by s squared plus omega squared to the power 2. All right? Now let us try to draw the pole zero polar of such a function. All right? So I see how many zeros do we have? So in order to be able to answer that question, you need to look at the numerator polynomial. What is the order of the numerator polynomial? In this case, n of s is 2 omega s. This is a first order polynomial, and when I equate this to 0, I would get s equals to 0, and I would have 1 0 here. Okay? What about the denominator? So d of s, the denominator polynomial is s squared plus omega squared squared. What is the order of this polynomial? What do you think the order is? So when I take the square, so that question is the same as what is the largest power that s gets in this polynomial? What is the largest power that s gets in this polynomial? And you will see that this is a fourth order polynomial when you take the square. Therefore, there need to be 4 poles of this Laplace transformation. Okay? In order to be able to find those poles, I would equate this polynomial to 0, and we see that whatever I find here, for each pole I find here, there will be 2 of them. Okay, because there is a square here, and this is the same as s squared plus omega squared equals to 0, and I would have s1 is equal to plus j omega, and s2 is equal to minus j omega. So I have found these two. Where is the rest? There are going to be 4 of them. Okay? So here what I have to do is to repeat these poles here. So S3 is at plus j omega, and S4 is at minus j omega. Okay? So the repetition is because of this. All right? Because of this square, there will be 2 poles at plus j omega, and there would be 2 poles at minus j omega. So here again we have poles on the imaginary axis, but in this case I would have multiplicative poles. So there are poles with multiplicity 2. All right? So if I obtain the pole 0 plot here, I would have 2 poles here at j omega, and I would have exactly at the complex conjugate here at minus j omega, I would have 2 more poles. Okay? So you see a pattern here. Okay? With the ramp function, with the unit step function, I had the following pole 0 plot. 1 over s. This function, this was the function 1 over s, and it had a single pole. Okay? What about the t multiplication here? The Laplace transformation was 1 over s squared. What was the pole 0 plot? There were 2 poles at the origin. With the unit step, I had a single pole, and with the unit ramp, with the t multiplication, I have double poles at the same position. What about the once more t multiplication? Then I would have triple poles at the same position. Okay? So each t multiplication is going to bring us a repetition of the same pole. Okay? Here I have the same thing. Sine omega t. Where were the poles of sine omega t? So sine omega t, the Laplace transform was s squared plus omega squared, and it had a pole 0 plot like this. Here a pole at j omega, and here a pole at minus j omega. And what happened when I multiplied that function with t? What happened is that the poles were repeated. Okay? So each t multiplication is going to bring a repetition of the poles. So then you can actually try to understand what happens if I multiply this t sine omega t once more with t. Okay? In that case, I would have t squared sine omega t, and actually that's going to bring us 1 more pole. So there will be triple poles here at plus j omega. There will be triple poles at minus j omega. Okay? That is what t multiplication does in pole 0 domain. So our final example in this property is going to be the following. And it is going to be f of t is t times e to the minus t sine omega t. I would first like you to think about what this function would look like. Okay? So I have a t factor which is increasing towards infinity, and I have an exponential factor. Is it a decaying exponential or a growing exponential? This e to the minus t is a decaying exponential. Okay? So if I try to draw these functions here, this is t, this is e to the minus t. And you know what sine omega t is looking like. Okay? So here, what is going to be the multiplication of these two? So when I multiply t with a decaying exponential, what is it going to do? Is it going to go to infinity? So here, in this course, you need to always keep in mind the following. Exponential always beats a polynomial. Okay, so t is a polynomial. It is actually a first order polynomial. Okay, and e to the minus t is an exponential. So when I multiply an increasing polynomial t with a decaying exponential, the decay of the exponential would always beat the increase of the growing polynomial. Okay, so this function would be looking like something like this. It is first going to increase a little bit, and then the exponential will beat the polynomial, and the result is going to be going towards 0. It is first going to increase just a little bit, but then it's going to decay towards 0. Okay, so we see here that this function t e to the minus t is a bounded function. It never grows towards infinity. It always remains bounded, and furthermore it decays to 0 as time goes to infinity. Okay? So when I multiply the amplitudes of the sine with this function, the amplitudes of the sine will never grow towards infinity. They will remain bounded. Furthermore, the amplitudes will decay to 0. So this function is going to be very, very similar to such a function. Of course, there would be differences with e to the minus t sine omega t, but because e to the minus t is always beating t in terms of growth, then I would have this function very, very similar in structure or in shape to this function, e to the minus t sine omega t. So if I just try to draw this function, then it's going to be very, very similar to something like this. It is first going to have some amplitudes, increasing amplitudes, but then it's going to have decaying amplitudes. Okay? So now the question is, what is the Laplace transform of this? What is f of s? So here I can again use the properties. But here there are multiple ways to use the properties. I can, for example, look at t sine omega t, and it's multiplied with an exponential. I can use that. Or I can look at e to the minus t sine omega t, and that is multiplied by t. So there are multiple ways to derive the Laplace transformation of such a function. So here I will write sine omega t is omega over s squared plus omega squared, and t sine omega t. So here that is going to be, instead of t sine omega t, I will write e to the minus t sine omega t. So this is going to be s plus 1 substituted instead of s here. So I have s plus 1 square plus omega square. Okay? It is coming from the earlier property here with the multiplication with the exponential. And here t times e to the minus t sine omega t is going to be the minus derivative with respect to s here of this function, s plus 1 square plus omega square. So I need to take the derivative of that function with respect to s once. So let us write minus d over ds. This is, omega is just a constant here, so I would put minus omega, and this is this polynomial to the power minus 1. S plus 1 square plus omega square to the power minus 1. Okay? So when I take this derivative, I would have the following. This is equal to minus omega. Minus 1 is going to come to the front. Minus 1 times s plus 1 square plus omega square to the power minus 2, and derivative of inside. Okay? Derivative of this polynomial with respect to s. And that is going to be 2 times s plus 1. So what is that going to give us? So the minus signs are going to cancel. I would cancel this one. And I would have s plus 1 here and 2s plus 1. That is equal to 2 omega s plus 1 divided by s plus 1 square plus omega square square. Okay? So now what happens when I try to draw the pole zero plot? The interesting thing here, I didn't have any zeros in those functions, in the earlier functions, sine omega t, e to the minus t, sine omega t, but there is a 0 in the last function, okay? So this is my f of s, and this 0 is at minus 1, okay? I would put a 0 at minus 1, and where are the other poles? So remember, if I didn't have square here, the roots of this polynomial would be at minus 1 plus minus j omega. Okay? Plus j omega, and I would have minus j omega. What does this square do here? What does it do to the poles? It is going to make them repeat. So there will be 2 poles here and 2 poles here. Okay? So we see again that t multiplication caused the repetition of the poles here at the same position. But it also caused an addition of a 0 here. All right? So here, what can I say about these pole locations? Their real part is negative. Their real part negative, what does it mean? It means that this function is going to be decaying towards 0, because this negative 1 is nothing but this minus 1 coefficient here. It's coming from this minus 1. That negative 1, minus 1 is coming from this minus 1 here. It is a decaying exponential, and it's going to beat whatever it has in the front. Okay? So the real parts of the poles tells us that the function is going to decay to 0 as time goes to 0. As time goes to infinity. And what does the imaginary parts say? Imaginary parts say that we will have oscillations with the frequency omega. The imaginary part, j omega minus j omega, tells us that there will be oscillations with the frequency omega. Sine omega t here. Okay? And what about double poles at the same position would say? It gives us the clue that there is a t multiplication in the front. So the real part determines this exponential e to the minus t. Imaginary part determines the frequency, and the multiplicity of the poles determines t multiplication. Before I continue here, I would like to emphasize that this same thing here, the exponential always beats a polynomial. This is also true for other things. For example, t squared e to the minus t. T squared is growing, e to the minus t is decaying, but the overall thing as t goes to infinity will go to 0. Okay? Because this decaying exponential will beat the increase of this polynomial. Okay? Whatever polynomial I have in the front of a decaying exponential is going to actually dominate the behavior of that polynomial. And it's going to make the function of time go to 0 as time goes to infinity. Okay? So as soon as you see poles in the left half plane, then it means that there are everywhere decaying exponentials. It means that the time function is going to go to 0 as time goes to infinity. If you see poles on the right half plane, that means that they are growing exponential. Their behavior is going to dominate every other thing in the system. So I would have growing oscillations in that case. The imaginary parts determines the frequency of the oscillations, this omega and minus omega. So the imaginary parts tells us that there are oscillations in the signal, in the function. And the repetition of the poles tells us the t multiplications. If there were 3 poles here, then I would know that there would be a t square multiplication in that function. Okay? So that completes the 4th property, and we're now going to go into the last property that we will see. So the 5th property. When all poles of f of s are either s equals to 0 or in the open left half plane. Open left half plane. We have the following. F of infinity is limit as t goes to infinity, f of t is equal to limit as s goes to 0, s times f of s. Okay? So I will first spend some time explaining this property. In mathematics, this property is called final value theorem. FVT. So it is, the name is obvious. It is the final value of the function. The value of the function as time goes to infinity, this is called the final value of this function. This final value of this function can be found by looking at the Laplace transformation of the function. If you don't know the function itself, if you know only its Laplace transformation, then you can still find what the final value of that function by looking at the Laplace transformation only. Without knowing f of t, if you know only capital F of s, then you can find the final value of that function using just such a limit. Okay? But there are some conditions for that. This is not always true. And the first part here, this text specifies when this is true. Okay? What does it say? When all of the poles of f of s are either at s, here maybe I need to write at s equals to 0 or in the open left half plane. Okay? So what does open left half plane mean? So I have the complex plane here, real of s, imaginary of s. I know that this is left half plane, this is right half plane. Okay? And what does open left half plane means? It means the left half of this space, but the imaginary axis is not included. That means the open left half plane. This is open left half plane. And open right half plane is the right half plane without including the boundary. Open left half plane is the left half plane without including the imaginary axis, which is the boundary. Okay? So then, for final value theorem to hold, for this equality to hold, there is a relationship between the time domain limit and then the Laplace domain limit here. For this equality to hold, the poles of f of s should be either at s equals to 0, they can be at the origin, okay? This is included. This point on the imaginary axis is included. Or they can be in the open left out plane. So either all of this or here. So here, therefore, I can actually try to draw the allowable region for the poles for final value theorem to hold. These parts of the imaginary axis are not included. Therefore, I will just draw them as dashed lines, but the origin is included. Okay? So this point is included. Just a single point here is included. And these parts are not included. Okay? And I would have this part, the origin as well. So this is the allowable region in final value theorem. So allowable region where the final value theorem holds. If the poles of f of s are in this region, then the final value theorem always holds. Okay? And now we're going to be looking at some examples. So here I will start a very basic example. F of t is equal to 1, t larger than or equal to 0. Unit step function. So I know that capital F of s is 1 over s. Do you think the final value theorem would hold for this Laplace transformation? Do you think this final value theorem would hold for this function, for the unit step function? And the answer is going to be yes. Why is that? It is because this function has a pole at the origin, okay? Here. And this pole is in the allowed region given in the final value theorem. Okay? So there is only a pole of that function in this region at s equals to 0 in the allowed region. Therefore, the final value theorem should hold for this function. Let us first calculate limit as t goes to infinity f of t, which is equal to 1. A very easy limit. Limit of 1 as t goes to infinity. This really doesn't depend on t. So this is going to be 1. What about this one? The other limit is s times f of s. Okay? And I need to take the limit of this thing as s goes to 0. Alright? And this is going to be limit as s goes to 0. So here you need to here realize that this is t goes to infinity. This is s going to 0. Okay? So you have the rough relationship, intuitive, I don't know if it is intuitive now for you, but you have the rough correspondence between t going to infinity and s going to 0. Okay? So this is s times f of s times 1 over s. These are canceling each other, and this is becoming 1. Okay? So you see that we have an equality here. This limit is equal to this limit. So the final value theorem is actually holding here. All right? Let us look at the ramp function. F of t is equal to t for t larger than or equal to 0. Unit ramp function. I know that f of s is equal to 1 over s squared. Where are the poles of this function? There are double poles at the origin. Okay? There are double poles at the origin. All of the poles are in the allowed region. Okay? So the final value theorem, I'm predicting that the final value theorem is going to hold here. Because all of the poles of this f of s are in the allowed region for the theorem. So now let us look at limit as t goes to infinity t. Final value of this function. I know that this is infinity. Okay? ramp function is growing indefinitely towards infinity. So this final value of this function is infinity. What about the other limit? Limit as s goes to 0, s times f of s. F of s is 1 over s squared. So this s is cancelling one of the s's in the denominator. So I would have 1 over s as s goes to 0. Okay? This is also infinity. Okay? And there is a match between these two values again. So the final value theorem is actually holding. Let us look at another example. F of t is equal to e to the 2t. All right? So what is the Laplace transformation of this thing? It was f of s is equal to 1 over s minus 2 or s plus 2. That is the question. So this is going to be s minus 2. If you remember. And where is the pole of this Laplace transformation? The pole of this Laplace transformation, there is a single pole, of course. That is why I'm calling it the pole. And there is a single pole. It is at s equals to 2. This pole is here in this region. So what can I say about all poles of f of s? Are they all in the allowed region? The answer is yes. The answer is no, because one of the poles is outside this allowed region. Therefore, the final value theorem will not actually hold here. Let us try. Limit as t goes to infinity, e to the 2t is infinity. This is a growing exponential as time goes to infinity. Okay? Now let us look at the other limit, Laplace domain limit. Limit as s goes to 0, s f of s. S times 1 over s minus 2. Limit as s goes to 0, s over s minus 2. Take the limit of this ratio as s goes to 0. What is that? S minus 2 is going to be minus 2, and s is going to be 0, so this is going to be 0. So you see that in this case, this limit did not really match this limit. Why did this happen? It happened because some of the poles of this Laplace transformation are outside the allowed region for the final value theorem. So the final value theorem did not really hold here. Let us look at this example. F of t is equal to cosine 2t. Okay? So we have just this function. This is for t larger than or equal to 0. So you see that I have forgotten here to write t larger than or equal to 0. You have to put them in your mind. I am really sorry. So here I have cosine 2t, t larger than or equal to 0. Do you think the final value theorem will hold for this example? You have to look at the poles again. And remember what the Laplace transformation of this one is. S over s squared plus omega squared. What is omega squared? Omega is 2 there, so I have 4 here. This is my Laplace transformation. Where are the poles? So I have s squared plus 4 is equal to 0. So s is equal to plus minus 2j, 2i. So the poles are at the following locations. They are on the imaginary axis, here and here, 2j minus 2j. Okay? So do you think they are in the allowed region for the final value theorem? So do you think they are here? The answer is no. They are just right at the boundary. And I know that the boundary is not included here. Okay? These poles are here, and these boundary points are not really included in the allowed region. So the final value theorem will not hold for this example. So here, what is the final value of this function? Limit t goes to infinity, cosine 2t. What is this limit for this function? This is a pure cosine. So it is always oscillating. While it goes to infinity, it still oscillates. That means that this limit does not exist. Does not exist. So do you think the S limit, the limit in the Laplace domain, do you think it will exist or not? So let us look at that. Limit S goes to 0, S times f of s, S over s squared plus 4. And as s goes to 0, this is s squared over s squared plus 4. As s goes to 0, this is going to go to 0. Okay? So you see that we again have a mismatch between these two results. And the reason for this is that there are some poles on the imaginary axis which are not allowed in the final value theorem to hold. Okay? So the final value theorem does not hold for this example either. So I have now finished the topics that I'm going to cover in this lecture. And what I'm going to do now in the last 5 minutes maybe is to tell you what we are going to do in the next lecture. Okay? So here we have seen some properties of the Laplace transformation, and the next lecture is going to be devoted to taking inverse Laplace transformations. So I would have, for example, I would give you an f of s, which is going to be looking like this, 1 over s plus 1. So you see that this really doesn't look like any of the Laplace transformations that we have seen today. Then how can I take the inverse Laplace transformation of such a function? We're going to see a tool that is called partial fraction expansion. And actually, what we're going to do is, in order to be able to take this inverse Laplace transformation, so we are wondering here about f of t. What is the time function for this? All right, I want to go back from the Laplace transformation. So I have to take inverse Laplace transformation here. And in order to be able to take such an inverse Laplace transformation, I need to be able to write this function, this Laplace transform, in terms of some Laplace transforms that I know the inverses of. Okay? So in the next lecture, we are going to see that I can actually write this Laplace transformation like this: a over s plus b over s plus 1. This is called partial fraction expansion. We are going to see the details in the next lecture. But do you think this is useful? There is an equality here, and instead of taking the inverse Laplace transform of this complicated term, I'm going to take the inverse Laplace transform of this one. But can I find the inverse Laplace transform of this summation? The answer is yes, because this is the very Laplace transforms that we have found in this lecture. Okay? So this is a times 1 over s plus b times 1 over s plus 1. So what is going to be the inverses of these? So I have f of t is going to be, this is the step function. This is the exponential e to the minus t, okay? So it's going to be a times 1 step function plus b e to the minus t for t larger than or equal to 0, okay? So you see that, and what is the intuition that I can get here? I see that this Laplace transform had some poles. Where are its poles? Its poles are here at the origin and at minus 1. Okay? When you try to take an inverse Laplace transformation, the poles of the Laplace transform is going to be very, very important. And the poles are going to determine which type of terms you are going to have in the inverse Laplace transformation. A single pole at 0 means that you're going to have a constant, which is a multiple of unit step function. A single pole on the real axis, a single pole on the real axis other than 0 is going to mean an exponential. If it is on the left, then it's going to be a decaying exponential like this. If it is on the right, then it's going to be a growing exponential. Similarly, if I have f of s is equal to 1 over s squared plus 9. When I have something like this, I'm going to be writing this Laplace transformation. In order to be able to take the inverse Laplace transformation, I will write this as a over s plus bs plus c over s squared plus 9. Okay? We will see the details of this procedure called partial fraction expansion. But it's going to give me something like this. Then what is going to be the inverse Laplace transformation? I will be able to say, by looking at the poles, imaginary s, real s, where are the poles? One pole is at 0. The other poles are here and here. 3j minus 3j. Okay? A single pole at the origin. What does it mean? A single pole at the origin means a constant. This is going to be my constant in the Laplace domain. And poles on the imaginary axis, conjugate poles on the imaginary axis, they're going to mean sine and cosine. And actually they're going to mean sine 3t and cosine 3t. So we're actually going to have f of t in the following form. A constant, plus some b prime coefficient, cosine 3t, plus some c prime coefficient, sine 3t. These c prime and b prime in general will not be the same as b and c. Okay? We will see the details. But by just looking at the poles of the Laplace transform, we will be able to say what type of function we would have in the time domain. So once you gain this intuition, when you look at a Laplace transform, you would be able to say which type of time functions we would have. And the rest of the course is going to be much easier, I promise. So that is going to be all for this lecture. In the next lecture, we will see inverse Laplace transformation and the partial fraction expansion. But that is all for this lecture. Thank you very much.